Well, this should be fun. Let's compute the equivalent capacitance of this network of capacitors. And upon first glance, it looks like it might be a little bit formidable. But we'll see that because of the values chosen, it will be quite straightforward. So we're going to compute the equivalent capacitance between A and B, and then also what's the charge on the three capacitors nearest A and B, these three capacitors, when 840 volts is applied to it. All right, so, well, when we reduce a network down, we have to start on the outskirts. And so here's the outskirts, so to speak, of this network. And if you look at this, these three are in series with each other, but that leg is in parallel with this leg, so it's in parallel with this 6.2. So let's figure out the series of 3. 1 over C equivalent is 3 over 9.3. 1 plus 1 plus 1, which gives us 3.1 microfarads equivalents. So this whole branch across here then is a 6.2 in combination with a 3.1. Those are parallel, so they add together directly, giving us 9.3 microfarads. So that 9.3 microfarad capacitor now is this whole thing. Oh, but that's originally what this outer one was. So immediately we see a pattern emerging. We have this reducing down to a 9.3, so there's a total of 3 occurrences of that. We just need to do it 2 more times. And we end up at the end with the equivalent capacitance is 1 over 9.3, 3 times, giving us a total capacitance of 3.1 microfarads between A and B. Isn't that fun? Wasn't that enjoyable? Now, let's see what the voltages are, potentials across the first 3, and what the charges are. So here we have, between A and B, 840 volts, and this is the functional equivalent of those first 3. Because even though this is really 6.2, when combined with everything else that's out here, it's like a 9.3. So each one has a third of the voltage, or 280 volts, across it. Then the charge of a 9.3 is very easy to discover. Capacity times volts, 0.0026 coulombs. Now, that's the same voltage that's across this capacitor. So even though functionally with all these other capacitors it's like a 9.3, it's really 6.2. So what's its charge? Its charge will be a little bit less. It's going to be 0.0017 coulombs. And the difference between these two is the amount of charge that's on the rest of the network. But that satisfies the requirement of the problem. Well, here's an interesting variation to a regular parallel plate capacitor, because we've got the region between the plates split up between 2 dielectric constants, K1 and K2. So different materials in each one. So that's going to alter the electric field across this region and in the region of the dielectric constant. So we have to treat this kind of separately. Now the first thing to ask yourself is this capacitor, these two segments, are they in series with each other or parallel with each other? And the answer is, from the point of view of across the capacitor, how many paths do you have? And you see we have 2 separate paths. Even though the current doesn't flow there, we have 2 paths for the effects across that give it its capacity. So in fact, it's in parallel. So let's treat it that way. Then, the entire capacitance is just the addition of the 2 halves, which is 1/2. Now why 1/2? Because the area is 1/2 for each one. So 1/2 epsilon A over D, but epsilon is the epsilon corresponding to the dielectric constant, so we subscript it 1, and the other one is 1/2 epsilon 2 A over D. Now the epsilons are based on the dielectric constant, so we can expand epsilon 1 and 2 to epsilon 0k. So epsilon 0k1, a over 2d, plus epsilon 0k2, a over 2d. And we combine these together, notice we have an a and 2d and epsilon 0. That factors out of both. Giving us our answer, epsilon 0 a over 2d, k1 plus k2. So that is the resultant capacitance of this capacitor that's split with two dielectric constants in parallel with each other.